Good morning, and let's talk about symmetries of functions. Here we have a parabola, y equals x squared. To determine if a graph is symmetrical to the y-axis, here's your y-axis. Picture folding it along the y-axis. If every point on one side of the y-axis has a corresponding point on the other side, every point, 0, 0 is symmetrical to itself. But if this is perhaps the point 2, 4, y equals x squared, and this is the point -2, 4, and every point has a corresponding point on the other side, then it is symmetrical with respect to y. Now, we use this phrase with respect to so much in math that it's not unusual to see it abbreviated like this, with respect to. Since every point on each side of the x has to have the same y value, so +1 and -1 have the same y, +2 and -2 have the same y. To determine algebraically, change x to -x in the equation. And see if it changes. If we look at this function, y equals x squared, and we write it as y equals -x squared, because -x squared is still x squared. No change indicates that it is symmetrical with respect to the y. Let's look at another example. Here's the graph of x equals y squared. So notice that for every x, let's don't use 1 and 1 since that doesn't help much, but let's say the point 4, where x is 4, two squared gives us 4, so this graph would contain the point 2. Sorry, it would contain the point 4, 2. When x is 4 and y is 2, you get 4 equals 2 squared, which is true. It's also true that if x is 4 and y is -2, x is going to equal y squared. So in this case, we're looking for points where there are corresponding points on both sides of the x-axis to determine if a function is symmetrical with respect to the x-axis. Imagine folding the graph along the x-axis. If each point above the axis has a corresponding point below the axis, then it is symmetrical with respect to x. Need to notice something. It cannot be a function. The definition of a function is that you cannot have an x value that has more than one y value. So in order to be symmetrical to the x-axis, it is not going to be a function. That doesn't mean it can't have an equation, but it's not a function. If we replace the y with negative y, so we get x equals negative y squared. That is still the same as x equals y squared, since a negative squared is positive. So since this is the same, that shows algebraically that it is symmetrical with respect to x. Now you can be symmetrical with respect to y and be a function, but if it's symmetrical to x, it's not going to be a function. There's a third symmetry we need to talk about, and that is symmetrical to the origin. If a function is symmetrical with respect to the origin, sorry, I left that out, what you want to do is turn the graph 180 degrees. If turning this graph 180 degrees and turning this graph 180 degrees, if you look at it upside down and it is still the same graph, then you can tell from the graph that it is symmetrical to the origin. Symmetrical to the origin means that every point has a corresponding point if you draw a line from the point to the origin and then keep going through the origin along the same line, the same distance. So let's say this is the point where x is 3, y would be 1/3. And this would be the point 1, 2, 3, negative 3, and negative 1/3. Because if we plug in a negative 3, we get negative 1/3. So notice that in order for this to happen, we have to change the sign on both the x and the y. If changing the sign of both x and y does not change the equation, it is symmetrical to the origin. Here, if we put negative x squared plus negative y squared equals 25, this still results in x squared plus y squared equals 25. Here, if we change the sign on both the x and the y, we get negative y equals 1 over negative x. But if we multiply both sides by a negative 1 to change this back to a positive y, so we can compare the two. If we multiply this by negative 1 and this by negative 1, we go back to y equals 1x. This is the same. This is the same. So both of these are symmetrical to the origin. So let's look at a couple of examples. And this doesn't write real straight, so you're going to have to use your imagination a little bit here. Let's say we had a graph like this. Is this symmetrical to x? No, because if we fold this along the x-axis, we do not get points that are both above and below. So it's not symmetrical to the x. Is it symmetrical to the y-axis? Yes. Every point over here has a point over here that corresponds to it. Every point over here has a point over here that corresponds to it. So this is symmetrical to the y-axis. Is it symmetrical to the origin? No, because if we turn this upside down, then we're going to get something along this line, which is a different graph. So it's not symmetrical to the origin. When they talk about even and odd functions, basically what that means is if it is symmetrical to the y-axis, it is an even function. Basically, it's called this because if a function has all even exponents, let's say we had y equals 3x to the 6th minus 7x to the 4th plus 2x squared plus 5. Without having to graph this, which would be a pretty massive effort, notice that all the exponents are even, and this is basically x to the 0. X to the 0, recall, equals 1. So since all of the exponents are even, if I plug a negative x in here, it's going to change it back to a positive x. So if all exponents of the x's are even, it's an even function. Now, I know you're going to be assuming that when I talk about odd, we're going to be talking about the x-axis. However, Turns out if it is symmetrical to the origin, not the x-axis, if it's symmetrical to the origin, it is an odd function. And this is basically because if all of the exponents are odd numbers, let's say we had y equals x cubed minus 5x. Now I can't put a constant in here. A constant doesn't change sign, but a constant would be the very next term. And to have odd exponents, it has to have alternate exponents. So this would have odd exponents. Notice that if I put in a negative y here, I'm sorry, if I change both the y to a negative and the x, that's the rule for the origin, right? I would get negative y here equals, this would become a negative x cubed. Negative times negative is a positive x. Now, if I multiply both sides by -1 to get it back to a positive y so I can compare the two, then negative x cubed times a -1 is a positive x cubed. Positive 5x times a -1 is a negative 5x. This is unchanged from the original. So an odd function only stays the same as the original if you change all the signs on both the x and the y. And that is going to occur if you've got all odd exponents. Now this applies when it is solved for y, so that you can put it in the function notation. There are relations that are not functions that are symmetrical to the origin, but they wouldn't be considered odd functions because they're not functions. So this relates only to functions. So if it's symmetrical to the y-axis, it's an even function. If it's symmetrical to the origin, it's an odd function. Anything else would be considered neither. Either it's not symmetrical to either of these, or it's not a function. Okay, so that's how it works with symmetry. It's not a real difficult concept. Don't let having to do it algebraically sometimes throw you, because basically it goes by the exponents. So you can usually tell at a glance whether a function is going to turn out to be even, odd, neither. So let me know if you're having any trouble, and I will talk to you later. Bye.